Good evening, dear student, and welcome back to the third part of this overview lecture on Lebesgue theory. Before we started during the last class, I think I said something here that I need to correct about UP. What I say here is that UP is less than or equal to N, but actually it's 1. I'm so sorry for that. I just realized, because if you just use N, you don't need to have N there, because if you take the limit when N goes to infinity, we are not sure, because this is an upper bound, but we need the actual value, right? So it's actually 1. It's true that N is greater than or equal to 1. So the upper bound still holds, but we actually need a value in this case. Okay, so how do we see that? Because this delta x is less than 1, right? So if I have delta x less than 1, n times delta x is less than or equal to n. But actually, this value is 1 because n is greater than or equal to 1. So you can see here k runs from 1 to n, so meaning that this n is greater than or equal to 1. But we want the actual value. Okay, so we can see directly from here that if our delta x is of equal size, the point of the partition are equally spaced. I have a problem with the screen. I can't see. I don't know what's going on with my computer. The screen is completely blank. I mean, it's black, and I can't really see. I don't really know what's going on here. Oh, okay. Yes, come back. I'm sorry for the inconvenience. Okay, so I was saying that if our points are equally spaced, delta will be the first point minus the last point, that is 1 minus 0 divided by the number of subinterval, which is n in our case. So delta x is 1 by n. And if you substitute 1 by n here, it gives us 1. So UP is actually 1. Okay, even if it is not equally spaced, we will get exactly the same result, right? Because the case where it is equally spaced is just a simplification, right? Now, if the points are not equally spaced, we'll have the sum of all the delta k. But now, what is delta k? Delta k is given by this value. This is delta k. Now, because the point of our partition are increasing, so we assume that xk is greater than xk plus 1 if you take an increasing sequence, and that should be the case, because if I partition from 0 to 1, the point of the partition are increasing, meaning that this delta k is actually xk minus 1. Now, if we sum all the xk, what do we have? So summation on k, when k runs from 1 to n, of delta k, it will be what? It will be this sum. So when k is equal to 1, we get x1 minus x0 plus, now when k is 2, we have delta 2 will be x2 minus x1. x2 minus x1 plus the next one will be x3 minus x2 and so forth, up to before the second last delta, which is delta n minus 1. So this will be n minus 1 minus n minus 2, x n minus 2. And finally, the last one, when k is n, we have x n minus x n minus 1. Now, you can see that this first term of the parentheses x1 will cancel out with the second term of the next expression. So we will do exactly the same thing here. This will cancel out with the next term of the second expression. This x3 will cancel out with the second of the next, and so forth. So everything will cancel out. So for any interior expression like this, we can see that the second component here will cancel out with the first term of the previous expression. So meaning that if I'm here, this will cancel with the second or the first term of the previous expression, so, which will be somewhere here. And this one will cancel with the second term of the next expression. So all the inner point, all these inner point, of course, when I say inner point, that is x1 up to xn minus 1, they will all cancel out, and we'll only be left with the second term, x2, and the first term of the last expression, xn. So meaning that this sum in total will give us xn minus x1. So that's what this sum will give us. But what is that expression? This expression will give us this is xn is actually 1. Sorry, this is x0, right? Okay, so and x0 is 0. And that's exactly 1. As we can see, where is that? Let us go back to the previous slide to see what is the value of x0 and what is the value of xn. Because these are the endpoints. We know that the first endpoint, which is A is 0, and B, the last point is 1, the interval 0, 1. So you can see from here that x0 is 1 and xn is 1. x0 is 0, sorry, x0 is 0 and xn is 1. So xn minus x0 is 1 minus 0, which is 1. So it confirms what I wrote here, and therefore we conclude that our U, the upper Riemann sum, right, with respect to the partition P, is 1. So that is to clear the confusion that I raised during the last presentation. Okay. So we mentioned in the previous presentation that in this subsection, we said that in this subsection, we state 3 fundamental results everyone must know. That's every student who is learning functional analysis should know. Namely, the monotone convergence theorem, which is also called Bepo-Levy, if I'm not mistaken, Fatou's lemma, and the dominated convergence theorem. Actually, what are these theorems all about? I think it was mentioned somewhere in the introduction, the difficulty that we had in the Riemann sum to take the limit under the integral sum. And we said that for that purpose, we need a uniform convergence result. But in Lebesgue theory, we don't actually need a uniform convergent result to take the limit under the integral sum. Under the integral. So these 3 theorems will allow us to know in which condition we can take the limit inside the integral. So the first theorem states that if Fn is a sequence of non-negative measurable and non-decreasing function, non-decreasing means that the function, the sequence of fk satisfies for any k in n, f sub k of x is less than or equal to f sub k plus 1 of x. So actually it's increasing. Non-decreasing means increasing function. So this is true for any x. And we assume that the sequence fm converges pointwise towards a function f for any x. Yeah, so this is called pointwise convergence. For each x, the limit of f nx converges to fx. Therefore, this theorem tells us that, actually, this is the monotone convergence theorem. We claim that we can take this limit under the sum, right? If you rewrite this last expression, this last result, replacing this f as the limit of the fn, we can rewrite it as limit of the integral of fn d mu when n goes to infinity equal to the integral. Now this f, what is f here by definition? F is the limit of the fn. So if you replace, we have limit of the fn d mu. So you see that if we read on both sides, actually we are taking the limit under the sum or under the integral. So if I take this limit under, it gives us this result. Or conversely, if we read from right to left, we can say that we are taking the limit out of the integral. Right? So either we are taking inside or we are taking outside, it's their equivalent. So this is what the monotone convergence theorem gives us. So in other words, if you have a sequence of non-negative measurable functions that are non-decreasing, and if that sequence converges pointwise towards a function f, then the limit of the integral of the fn will be equal to the integral of the limit of the fn. You can take the limit under the integrals sign. So this is what the monotone convergence theorem tells us. Right. And something that we did, something that was not mentioned here is actually that the limit f is integrable, because we cannot write this if the function is not integrable. So this function f actually is an integrable function, and we have this result. Am I right in what I'm saying? No, no, and no, and no, and no, and no. So at this stage, the function is just measurable because there's no integrability condition on the sequence. They are just measurable. But if beside the function fn, the sequence of function, each function is integrable, therefore the limit itself also will be integrable. Yeah, so that is the extra information that I need to specify. Okay, as an example, if you take x to be the interval closed at 0, open at infinity, and fn x is -1 by n for all x, then the integral of each fn will give us -infinity. But this function fn increasing. They are increasing. And they converge towards 0 if you take the limit of 1 by negative 1 by n when n goes to infinity gives you 0. So it will converge towards the constant function equal to 0. Right. So if you compute the integral of 0 is still 0. But the integral of each fn gives us negative infinity. Now, if we take the limit of this integral, it's still negative infinity. So we see that there's no equality between the two results. I mean, in this case, the limit of the integral of the fn d mu when n goes to infinity is negative infinity. And this is different from 0, which in turn is the integral of f d mu, where f here is the limit of the fn. So you see that the monotone in convergence theorem the condition of the hypothesis of the convergence monotone theorem, monotone convergence theorem are not satisfied, right? So if one of the conditions is not satisfied, we are not expected to claim the result. Why? Because here we can see already that all our fn are negative. That's the first thing. But in the monotone convergence theorem, we have the condition that the function fn are all non-negative. Even though the fn here are increasing towards f, as it is the case in the monotone convergence theorem, we don't claim the result. We cannot take the limit under the integral sign. We can't. You can see it from the result. So the hypotheses are very important. So when we claim or we want to use the monotone convergence theorem, we need to make sure that the hypotheses are all satisfied in order to claim the result. So let us look at another condition here. Now, if you assume that for each n, fn is given by n into the indicator function of the open interval 0, 1 by n, each fn is positive. So we have a sequence of non-negative measurable function. Why is it measurable? It's just measurable because if we denote by an, the open interval 0, 1/2, this is Borel measurable, right? So it's in the Borel sigma algebra. So consequently, consequently, the indicator function of a measurable function is a measurable function, and if you multiply by a constant, it's a measurable function. So this first condition, sequence of non-negative measurable functions, are satisfied. Is satisfied. That first condition, that first hypothesis is satisfied. Now, do we have the second hypothesis? Non-decreasing. Now let's look at our function. The fn do not increase towards f. So what is f? If we take the limit when n goes to infinity, the fn will convert towards 0. They will converge towards 0 for each x. So 0 is the limit. But are this function increasing towards 0? No, they are not. They are not increasing towards 0. So in that case, are we expecting the result to hold? Can we claim that we can take the limit under the integral sum? Let's check. Now, if we compute the integral of each fn, we obtain 1. Whereas the integral of the limit, which is 0, the integral of 0 is still 0. So we see that the limit of the Fn d mu when n goes to infinity, that limit is 1. But this limit 1, the limit of the integral, which is 1, is completely different from 0, which is the integral of the limit f, because that limit f is 0, integral of 0 d mu. So we see also in this case that we can claim the result of the monotone convergence theorem because one condition of the theorem is broken. That is, the convergence of the sequence increasingly towards f. So we don't have that condition. So I hope that with these two examples, each time we will be applying the monotone convergence theorem, you make sure that all the hypotheses of the theorem are satisfied before we claim the result. Okay, now that we have the monotone convergence theorem, we can now state the linearity of the Lebesgue integral. So if f and g are non-negative and measurable function, both integrable, then the integral of the sum is equal to the sum of the integral. Right. We are not going to prove it. Unfortunately, we are not going to prove it here. Proposition. So we suppose that Fn is a sequence of non-negative measurable function. Then we can interchange an infinite sum with the integral. So we can interchange. So we have the integral of a series is equal to the series of the integrals. So in other words, we are interchanging the sum with the integral. Okay, now to prove this, we can prove this by means of the monotone convergence theorem. We can prove it by means of the monotone convergence theorem. So in that case, how do we prove it? We can set, for instance, we can denote by maybe if we denote, let's say, S sub n like this, we take this to be the partial sum of Fn n running from 1 to infinity, to capital N. Since each function n, Fn, is integrable, is measurable, the final sum of measurable function will be measurable. And they are non-negative, this will be also non-negative. So the sequence of Sn is a sequence of non-negative measurable function. And we can see that this function is increasing. It's an increasing function, right? It's an increasing function. So why is it increasing? If you write S sub n plus 1, which actually will be equal to Sn, this one. Sn is positive, right? For any n is positive. So this Sn can be written as, actually is the sum n running from 1 to capital N plus 1. You can see that we can split this into 2. So if we split into 2, it will give us the sum up to capital N plus f sub n plus 1. So the sum till n gives us s sub capital N plus the last term, which will be f sub capital N plus 1. Now, if I take the difference, x sub n plus 1 minus s sub n, this gives us f sub capital N plus 1. But we know that each f sub n is non-negative, so this is greater than or equal to 0. So if it's greater than or equal to 0, it means that the sequence is increasing for any n. Because the sequence is increasing, now if I take the limit, this limit, right? We assume, of course, that if you write that, it means that this sequence converges. So if we call the sum of this, so if we note by S, the sum of the Fn, this sum, which is actually the limit when capital N goes to infinity of S sub n. So that is exactly what you have. So if you take the limit of Sn when n goes to infinity, it gives us this function f. And this function also is measurable. Why? Because it's the limit of measurable function. We saw that each S sub n is measurable as a finite sum, and the limit will also be measurable. So this f is also measurable. And we can use the monotone convergence theorem. All the conditions are satisfied, all the hypotheses. We have that the function, the sequence, we have a sequence, the S sub n form a sequence of non-negative and non-decreasing function. And the limit of the S sub n converge to f point-wise. Therefore, we can claim the theorem. So if we claim the result of the monotone convergence theorem, we conclude that, so we can claim the result by concluding that the limit when n goes to infinity of the integral of S sub n, right? This will be equal to I can take the limit inside will be equal to the limit of S sub capital N when n goes to infinity. But what is this? So this is the integral of that limit. This limit is the sum f, which is the infinite sum, n running from 1 to infinity. So this gives us the sum when n runs from 1 to infinity, f sub n, right? And what is this? It is the first one, right? Now, this side, because we have a finite sum here, you can always interchange Sn. This is Sn. So this other integral. So let me write this one. So this one will give us the limit of the finite sum n running from 1 to capital N Sn d mu, and we have the integral like this with a limit. So I can take the finite sum, I can take this finite sum from the integral. So if I take that finite sum from the integral, this will give us sum n running from 1 to infinity, the integral of f n d mu. Before putting the infinite sum here, we can write that sum here because I take this finite sum from the integral, and the limit will still be in front here. And by definition, if I write a finite sum and take the upper limit to infinity, this limit will give us the series, right? So this will be equal to this expression here will be equal to infinite sum, the infinite sum, n running from 1 to infinity, f sub n d mu. So as we said, this one is equal to the final one there. So this is equal to the integral with the infinite sum where n runs from 1 to infinity. So we end up here with the result of this proposition. So that's to show that the proposition is just a consequence of the monotone convergence theorem. So this proposition can also be called corollary. So it's a corollary. It's a corollary of the convergence with the monotone convergence theorem. Okay, so now let's move to the next slide. If the function f is integrable, then the absolute value of the integral is less than equal to the integral of the absolute value of f d mu. So the next theorem is Fatou lemma. What is Fatou lemma? For Fatou lemma, there is no condition on the. We just have a sequence of non-negative measurable function, no extra condition. Fn is a sequence of non-negative measurable function, full stop. No information about the function increasingly converging towards something. No, you don't have such a condition. So because of that, we are going to have an inequality with the limit inferior. So what is Fatou lemma theorem? So this is the statement of Fatou lemma. We suppose that Fn are all non-negative and measurable, then the integral of the limit inferior of Fn d mu when n goes to infinity is less than or equal to the limit inferior of the integral of the Fn d mu. Right. So this is the second theorem. The last theorem, which is known as the dominated convergence theorem, has a very fundamental consequence in the theory of integration, or Lebesgue theory. Very, very important. And I think that the proof relies on the monotone convergence theorem. I think so. So let's take the the dominated convergence theorem. So we state the theorem. Suppose that Fn is a sequence of measurable real value function, and that for each n, Fn converges to f of x. This is what we call pointwise convergence. Further, we suppose that there exists a non-negative integrable function g such that absolute value of Fn of x is less than or equal to gx for all x. So this conversion is what we call the dominance or the domination. We see that all the functions Fn are dominated by a single function g. So we conclude that we can take the limit under the integral sign. So now if we compare this to the first and the third theorem, that is the monotone convergence theorem and the dominated convergence theorem, what do we realize? What do we notice? We have that both function, in both theorem, the function are non-negative and measurable. Not necessarily. No. In our case here, we don't really require the function to be non-negative. They are just real value functions. Sorry for that. So, but both the sequence, in both theorem, the sequence is made of measurable function that converge pointwise towards a certain limit f. In the case of the monotone convergence theorem, the convergence is done in an increasing manner. And we can conclude if it converges increasingly towards the function f, we can interchange the limit under the sum. That is, we can take the limit under the sum, or we can take it out of the sum. The sum here is the integral. Now, in the absence of monotonicity, in the absence of the monotonicity of the function, or the fact that the function is increasing towards f, and also the absence of the positivity of the function, it is replaced by the dominance of the sequence of function by a measurable function, by an integrable function g. So that is the condition that replaces the missing hypothesis from the monotone convergence theorem. Okay, I think we are already at the end of this presentation. We can now talk about the application. The application of Lebesgue theory in modern science and engineering are ubiquitous. It is being applied, or it is used in the study of Fourier series, in the probability theory, and stochastic processes. It is also used in finite element methods. In the quantitative analysis of partial differential equation, etc. What is the quantitative analysis of partial differential equation? Quantitative analysis is when you want to solve a partial differential equation, you first of all need to prove the existence of the solution. Let's say the existence and uniqueness of the solution. Before you even try to compute the solution of a differential equation, be it numerically or analytically, you need to know whether the problem is well posed, the solution exists and is unique. And this is done through Lebesgue theory. That is, we first of all define the functional space in which we are going to seek our solution. And generally, those functional spaces are subset of LP, or the LP spaces. So that's why they are really important. So for those who are interested, the references that I used to write this presentation, or to write these notes, are the following. The first one is Apply Function Analysis by Tinsley and Demkovich. The second one is Hawkins, Lebesgue Theory of Integration, Its Origin and Development, Volume 282, published by the American Mathematical Society in 2001. And the last reference is by Pilstrom R. Lebesgue Theory, A Brief Overview, published in 2016. Okay, guys, thank you for your kind attention. God bless you. And I think before we part, maybe I need to do some exercises. Or maybe we can do that in the next presentation. Okay, so I'm going to solve, we are going to look at some application. How can we apply some of these results? Example 1. I think I'm encountering another problem here. Oh, so my screen is completely black, so I can't see anything, so I can't even write. Okay, I think I will stop. I will stop. I will stop the presentation and start a new one. So it's better to save at least this. Okay, let's see if I can use it. Yeah, it's better to save this one first before we get into a mess, right? So let me save this, guys. So we will meet again in a few minutes. We are going um, to record another video, which will be just the application of the Lebesgue theory. So guys, thank you for your kind attention. God bless you and see you very soon.